Hi, in this video I'm going to be focusing on concentration units, especially molarity, which we use a lot in chemistry, and this is section 5 out of chapter 4. So the concentration of any solution can be expressed many different ways. Some of the ones that you may have heard of before are things like gram per milliliter or part per million or percent. But one thing to keep in mind is no matter what units we're using, these are expressing the amounts or masses of solute dissolved per mass or volume or amount of solvent. And really the one most important unit that we'll be using a lot is molarity. And you can see the word mole is in the word molarity, and it's useful because it relates the number of moles to the volume of the solution. So we'll go through a couple of examples of what that really means throughout this lecture. So specifically, molarity is the number of moles divided by liters of solution, or you can abbreviate that as M equals little n over big V, number of moles over volume. Keep in mind that volume does have to be in liters. And just kind of how we use the terms, we'll often call a solution by the molarity, but abbreviated as molar. So you might hear about 1 molar HCl or 0.5 molar sodium hydroxide. And molarity and molar are both abbreviated with a capital M, so you'll see that on chemical bottles, NaOH 0.5 M for molar. So before we go into many calculations, I just kind of wanted to give a conceptual demonstration of how this all works. So you'll see in this beaker I have a nickel chloride solution, and these little buttons over here allow me to change the amount of solute and the amount of solution, or the volume of solution. And then this slider over here shows what the resulting concentration is for this particular solution. So when I only have 0.06 moles of solute divided by, or in 0.87 liters of total solution, my concentration is only 0.07 molar. Now, when I raise the amount of solute, you'll see my solution getting to be a darker green. Green is the color of the nickel chloride solution. And yeah, as I put more and more solute in there, my concentration gets greater and greater. So let me slide it back to only a relatively small amount of solute again. I can also make the concentration greater by having less water, by having less total solution volume. So if I have the same amount of solute, but I reduce the total volume, my solution will get more and more concentrated. Now, you can't just kind of play with these sliders ad infinitum. If you have a lot of solute, more and more moles, eventually you can hit a solubility limit. In which case, if I have a full mole of solute, but only a very small amount of the liquid, I may start to hit upon that solubility limit. Now, that's not the case for this nickel chloride, but let's look at let's look at copper sulfate instead. If I have the same amounts with copper sulfate, I see that my solution is indeed saturated. If I were to increase the volume, eventually all of this copper sulfate will dissolve, and I'll no longer have a supersaturated solution. So in this little simulation, you can see that the max concentration of copper sulfate in solution is 1.6 molar. Okay, so back to the rest of the show. What can we do with this knowledge about molarity and concentration units? There's a number of things. First thing is we can make solutions in the lab. That's a common thing that we need to do in chemistry. We can calculate how many moles of solute there are given any volume of solution. Once we know the molarity. There's kind of other permutations of this question as well. And from that, we can do solution stoichiometry. Stoichiometry involves relating the molar amounts of reactions and products. So you can kind of see where this is going. If I know how many moles are in my given volume of solution, I can use that to do some of the stoichiometry problems that we've been working on previously. I can also do dilutions, which I won't talk about here, but we'll talk about in class. So yeah, making solutions. If I want to make a specific molarity, what I do is measure out the correct number of moles. And so let's say that this is a 0.75 molar solution. Oops. 0.75 molar solution. That means 0.75 moles for every 1 liter. And so, yeah, what we're showing here is down here we got our 0.75 moles of some compound, and I'm pouring in enough water to make 1 liter. So keep in mind that volume, that liter on the denominator of the molarity, is the total volume of solution. And so if this is a 1 liter flask, I want to fill this flask up with enough water to come right up to that 1 liter line. And of course I would read the bottom of the meniscus to get an accurate reading. Okay, so let's run through some calculations. If I have 0.1 moles of HCl and I mix it with enough water to make 250 mils of solution, what is the resulting concentration? Well, what we want to do is go back to that formula that I was talking about previously, and that is that molarity equals the number of moles divided by volume in liters, and substitute into that value. Now, since this volume is in liters and our given volume is in milliliters, we're going to need to convert that. So 250 mils to liters. We want mils to cancel out, and we want to get this value in liters. So there, in one mil is equivalent to 10 to the minus third of a liter, and so that gives us 0.25 liters. So back to this formula. Yeah, if I have 0.1 moles, I substitute that in for N, and I divide that by 0.25 liters. And now I just have to do out the math. That gives me a molarity of 0.4 molar. Let's look at this a slightly different way, just using the same formula, but kind of in a different manner. Here, I want to, if I measure out some volume of a solution of a given molarity, how many moles of, in this case, nickel nitrate do I have? So what I want to do here is I can kind of set it up the same way. Molarity equals N, little n, number of moles divided by volume, again in liters. And so here I know my volume and I know my molarity, but I'd be solving for N. So if we rearrange this, I can see that N is equal to M times V. And so at this point I can just substitute in. The number of moles is equal to 0.200. And when I use molarity, rather than writing the capital M, which would be correct, I like to express that in what that unit really is, and that's moles per liter. And that will allow me to cancel out my units and know that I'm doing everything correctly. So I multiply that by 0.022 liters, and yeah, see here, I can see now that my liters are going to cancel out, and that'll give me moles. That will give me 0.0044 moles of the nickel chloride. And you'll see I took two significant figures in this calculation because my volume here had two significant figures. Okay, so I think you can probably see where this is going. Previously, we had the stoichiometry map where I compared, you can compare your mass and calculate moles from your mass using molar mass, and then use a mole ratio to compare any reactant or product in a balanced chemical equation. So we are just adding one more wrinkle onto this map, and that is that we can also calculate moles, as we just did, from the volume of a solution if we know the molarity. And so we can use molarity like a conversion factor, and we can do the same on the unknown side of the stoichiometry map. So let's look again at that question, that previous problem that we just worked on. If I have 0.022 liters of 0.2 molar nickel chloride, now let's say I want to react that nickel chloride with sodium phosphate to produce nickel phosphate. The balanced chemical equation for this reaction is here, and always good to kind of look at your ratio before you even start. My given material is the nickel chloride, and my unknown is the sodium phosphate. So this ratio of 3 moles nickel chloride to 2 moles sodium phosphate is definitely going to be important. So question is, what volume of sodium phosphate would I need to react all of the nickel chloride? Now you can't answer this question unless you know the concentration, and luckily the concentration is right there, 0.050 molar. Okay, so just repeating some of the information here and talking about strategy. My strategy here is that I definitely want to convert the given to moles. As I've said in class to at least some of you, this is a really good first step for any stoichiometry problem. Anything that's given to you needs to be in moles. I'm next going to use a mole ratio, just like we've done with previous stoichiometry problems, to determine the moles of the unknown. And then lastly, I'm going to use the formula for molarity again to determine the, that should not say formula there, but to determine the volume needed of the sodium phosphate. And yeah, again, I'm going to just kind of take this path on the stoichiometry map. Volume to moles via molarity, moles to moles of given to moles of unknown using a mole ratio, and then using that molarity formula again to calculate the volume of the unknown solution. So yeah, the first step in this problem is to convert this volume to moles, which we did in the when I first introduced this problem, but now I'm going to show you just kind of a different way to think about it. You can use molarity like a conversion factor, and the math is exactly the same, but I can set this up and say that in every 1 liter of solution there are 0.200 moles, and so using that allows the liters to cancel out. Mathematically, we're just doing the same thing as plugging into the molarity equals moles over volume formula. But so we get the same value for the moles of nickel chloride, 0.0044 moles of nickel chloride. Okay, now the next step is I'm going to take that molar amount of nickel chloride, moles of nickel chloride, and compare it to the moles required of the sodium phosphate using the mole ratio. So according to that balanced chemical equation, for every 3 moles of the nickel chloride, I need 2 moles of the sodium phosphate. Oops, that's pretty messy there, but you can tell what I'm going for. 2 moles sodium phosphate for every 3 moles of nickel chloride. So really I'm just taking 2/3 of 0.0044, and that comes out to be 0.0029 moles of the sodium phosphate. And then lastly, let's use the formula this time. Molarity equals moles over volume. And the problem said that our solution that we have is 0.050 molar. So that value gets plugged into the molarity, and the molar amount that we've calculated that's needed gets plugged into for little n. So let's rearrange this a little bit. If we cross multiply, we get Vm equals n. And then if we want to isolate V, we'll divide both sides by m. So volume equals n over molarity. And yeah, substituting in, volume equals our 0.0029 moles divided by our 0.050 molar, and again you can break that molar unit into moles per liter, and that shows that moles cancel out and liters would flip to the top of this particular problem. So yeah, this gives us, this division gives us 0.05867 liters, and we only have two significant figures in some of these measurements, so this would round to 0.059 liters or 59 mils. So that's a stoichiometry problem using concentration and molarity.